Here we are at Bird Rock in the intertidal zone, and you can really see the diversity of habitats that we have here. So first of all, we're starting up in the high intertidal zone, where we have a very low diversity of animals in general. We have a lot of tough algae that can resist desiccation and heat stress in this area of the intertidal, as well as a lot of lichens. However, if we go forward, we can see some of our other microhabitats that we have here in the intertidal zone. Another one would be cobble. Cobble are going to be these loose rocks that you see here. They're sort of scattered around the intertidal zone. Cobble is a great habitat for many organisms because they can hide within the crevices of the rocks. And these rocks tend to retain water underneath them. So these organisms can actually remain wet and moist and get oxygen even if they're in the high intertidal zone because they're in these cobble habitats. Another microhabitat are tide pools. There's a large one. Small tide pools over here. Tide pools, of course, are going to be always wet unless we have extreme heating, like in the summer perhaps at a very, very low tide. But generally speaking, they'll retain water for the entire time, the existence of the pool. And obviously this is a great microhabitat for many organisms to, again, resist being able to drying out, as well as having heat stress and problems retaining oxygen. Finally, if we look over in the distance at Bird Rock, we can see the bare rock that surrounds that area, really devoid of lots of life. That's ledge habitat. Here's a little bit also beneath my feet. It's basically flat rock with maybe a scum of algae and sediment on top of it. But other than that, it doesn't have a lot of living organisms. This is a very inhospitable habitat because of the heavy wave action that can come across this area, as well as the fact that the sun really beats down on this area, on this habitat. So organisms cannot really resist drying out and getting heat stress very easily. So those are our three basic microhabitats. Ledge, like you see here. Tide pool, you see here. And then cobble, that is the sort of small rocks and boulders that we see sort of interlaced within the ledge area. All right, we're going to talk about sampling in the intertidal now for a few minutes. Hi, Carl.
Hello, everybody. Right. Sorry you're not here.
Yeah, sorry about that. Anyways, better safe than sorry. So we're going to illustrate how we go about sampling the rocky intertidal zone. So here's our equipment. We've got a quadrat with lines tied in it so we can make different sizes or areas that we want to sample. We've got a transect laid out here, transect tape going from the low to the high intertidal zone. And I've got a clipboard, and of course we would collect data on our clipboard if we count things, but we also have a random number table, and this is going to become important in just a minute, and we'll explain how we do this. So we chose to lay our transect out in a sort of vertical direction. So as we're going to talk about in class, even though we're in a very flat area here in the intertidal zone, ecologists think of the intertidal in terms of low to high intertidal. So the high intertidal is back away from the water. The low intertidal is over here in the direction of the water. And so we chose to lay our transect out in a sort of perpendicular direction. So we're in the low intertidal working towards the high intertidal. And that allows us to see how the density and diversity of organisms changes as we go from this area in the low intertidal with stressors like predation, competition, and wave energy to the high intertidal where we have many other stressors like lack of oxygen and drying out and desiccation and heat stress and things like that. We could also have chosen to sample different zones by putting our transect in a horizontal direction. So it would have gone maybe in the high intertidal for a transect and then moved down here to the low intertidal and so on. So that's another option we could do as well. So what we're going to do is we're going to demonstrate random sampling. This is a really, really key idea in sampling. Any place you're going to sample in ecology, random sampling is key. It turns out that people are really, really good at unconsciously biasing themselves to sample particular areas. So Carl loves marine organisms, and he's down here, and if we were just let him go off and sample wherever he wants to, he's going to pick the coolest areas to sample. And then he's going to get tired and lazy, and then he's going to pick the easiest places to sample. All right, so we're going to have extremes. We're going to have some data in places where there's tons of organisms to look at, and then we're going to have some data in places where there's nothing. We have to randomly sample so we don't unconsciously bias ourselves as we do sampling. So we have our transect. We're going to start here at the end. And what I'm going to do is I'm going to use my random number table, which, believe it or not, is a list of numbers in random order. And I'm going to put my finger down on this table, and you have to imagine this because I can't hold the camera and the clipboard at the same time and do that. But I'm going to find a place, let's say where my thumb is. I'm going to read across, and I find the number 2. I came across the number 2. So Carl's going to take 2 steps, 1, 2, in the direction of the high intertidal. 1, 2. He's going to stop there. Then we're going to pick another place on our random number table, and we're going to find our first number between 1 and 2. So let's see, I go over here, and what did I land on? I landed on number 1. Number 1 means Carl goes to the right. And he doesn't go yet because I'm going to pick the number of steps he's going to go. So I'm going to go to another place on my table, and let's see, right over here, and I have the number 5. So he's going to take 5 steps over to the right, 2, 3, 4, 5, and that's where he's going to put his quadrat down. All right, so that gives us a randomly located spot where we can't bias ourselves by picking a place that's really cool or really lame. Now, let's look at the transect, or excuse me, the quadrat. So here's our quadrat, and you can see it's gridded. And this is really important because for some organisms, they are super abundant, like say little barnacles. You might want to use only one little cell in this gridded quadrat. Believe me, there can be thousands of little barnacles within one of these little cells. For other organisms, like maybe big limpets or anemones, you might want to use the entire square meter to count things. So we have our options here of what areas to sample depending on what organisms we're looking for. And as we're going to look at in class, the choice of the area in which to sample can greatly influence how many species you find when you're doing your sampling. Right? The larger an area you sample, the more you tend to find those rare species that are just not very abundant, and therefore usually find a higher species diversity. So the choice of a quadrat size is very important to think about when you're sampling the intertidal. You'd obviously want to sample the largest quadrat you can so you can find the most species that are here. However, at some point it becomes almost impossible to collect a lot of data because a large quadrat like this might take many, many hours to count if you're looking for really tiny little organisms. So let's wrap this little segment up by looking in detail down here at one of these cells this quadrat landed on. We can see underneath we've got lots and lots of algae. We can see right away. And we've got all kinds of things, and most of those things are going to be under the rocks. So if we go ahead and we sort of pick up rocks, we're going to find that we have lots of organisms that are underneath. Thank you, Carl. Some of these rocks, like chitons.
Oh yeah.
Chitons, very, very common organism to find on the underside of these rocks. All right, these are large chitons, as you can see. Very different than the ones we showed you in another video where we found them with a territory down etched into the rock. These are ones that are much more mobile, and you can actually see them moving very slowly if you look carefully.
Oh, there's a weird worm down there.
And these chitons are going to be found almost exclusively underneath the rocks where they don't dry out, and they're protected from predators as well. And here we are. We used our random number table to arrive at a place to sample in the intertidal zone in a cobble area. And this is a good illustration of a time where you not want to use the entire quadrat to sample, because if you look closely, you'll see all kinds of little organisms like periwinkles in this area, right? We've got lots of limpets that are over here in this area, and these are small organisms that if we were to try to count every one of them in this large quadrat, it would take us simply forever, especially if we think about lifting up the rocks. Say go.
Go for it.
All right, so in this instance, we'd use maybe a quarter of this quadrat, this area here, so a quarter square meter, basically, to try to count things. We could even use only one cell of this if we find super abundant organisms. Sometimes barnacles settle en masse, that is, they settle basically gregariously, all in the same place. We might have literally hundreds of little tiny barnacle juveniles in one little cell. Here I would probably choose to sample a quarter of the square meter and count the periwinkles that we find within that area. And it still might take us quite a little bit of time to do that because they're so abundant. Another thing to point out in this particular area in which we landed is Serpulorbis. Serpulorbis are these snails. They look like worms, but they're actually snails. Snails that colonize primarily the underside of rocks like you see here. And in class we talked about gregarious settlement. Settlement that occurs for organisms on top of one another because they're cued into cues that allow them to find a good habitat. So if you know some of your fellow species, fellow individuals in a species have found a good place like the underside of a rock, cueing in on the signal, the chemical signal from those organisms is a good idea. And so the serpulorbis are found in these large colonies with all these tubes going every which way from gregarious settlement.
Now that we've talked about how we do our sampling, we'll just kind of go through the intertidal and give you a quick tour, starting at the upper intertidal and working our way down to the lower reaches.
Here are some more organisms adapted to the high intertidal. So if I pan out, you can see we're actually pretty far from the water, and this is up really high on top of a ledge of rock. And here we have Litorina, so we have periwinkles. And you can see, first of all, they're all clustered in this little scar, or sort of break in the rock. And you can see that also they're light in color. So, of course, these organisms have to worry about drying out. They have a shell that can close very tightly with an operculum to prevent that. They have to worry about getting really hot. The sun beats down on these rocks, especially in the summer. And they're light in color to help deal with that. They also have a very, very small sort of footprint. They are attached to this rock, but very lightly. In fact, you can sort of take them off really easily because they don't want to maximize their surface area that's on their attachment to the rock. They want to minimize the amount of their body that's attached to the rock. So they're actually quite easy to dislodge. But of course, waves don't come up this far, really. So they don't have to worry about mechanical stress, just about the stresses of the high intertidal zone. Here's another adaptation to drying out or heat stress and things like that, and that's being mobile. Not all organisms are attached and sessile or sedentary. Some of them can crawl around and find their own microhabitats. It's a sea roach. Here, basically, it's a kind of isopod that's right now in a little crevice and sort of ignoring me. And I'm going to try to get it to move, and there it goes, running away. So finding your own little microenvironment is obviously another way to deal with the stresses of the intertidal. Okay, here we are in the high intertidal, well away from the water. And we're going to find another organism that's got a great adaptation to this area, and that is solitary anemones, also sometimes found in colonies, as we're going to talk about in class. So here is one that's still in the water a little bit. You can see the tentacles right there, and if I poke at it, you'll see it goes in a little bit. It doesn't like being disturbed. And there's other ones that are around here, and these are a great illustration of adaptations for the high intertidal where there's a lot of heat stress and desiccation, or drying out. And you can see how these things cover themselves with bits of shell and rock. And that, of course, helps beat back the sun, or prevent the sun from heating up too much. And also keeps them camouflaged, so in case predators come along. And also helps retain moisture. The little cracks and crevices and all the little bits of shell and pebbles on top of this animal helps retain water, so that the ones that are out here exposed on the rock at a low tide like we have right now are actually going to do just fine, like the ones that are also found in these tide pools, little tiny tide pools. Okay, so here we are in a ledge habitat, and if you look in closely at this ledge habitat, you see there's areas of flat rock, and then there's all these bumps which are juvenile barnacles. And these juvenile barnacles have all settled here in this large group. And some of them are open at the top, which means that they've either been eaten or they've died from other sources. And the shells are left. Others are closed, which means that there's still a live animal in there. And they've sealed themselves up at a low tide, so they retain water and oxygen, and also don't dry out. So this is a great illustration of space competition. So these barnacles are small at the moment, but they are, of course, trying to grow. And as they grow, they're going to start running into each other. And you can see some of them already very, very close to the others around them. And this is our primary limiting resource in the intertidal zone, the rocky intertidal zone, is space. So these barnacles will begin to compete for space as they grow. Some of them will grow under others and actually pry them off the rock in very, very slow motion over time. Another thing this is really good to illustrate is going to be the danger of settlement. So we talked about settlement and recruitment in class, and we talked about the fact that at the time of settlement, when these organisms are very small, it's very dangerous for them. And that's because organisms can come along and easily get into their shell and consume them. But also some predators are really, really good at finding these areas of very dense aggregations of individuals. So when these barnacles settle in these huge areas, some predators like gastropods that come along and can actually crack open the shell or dig into the shell are able to find these areas and consume lots and lots of these little mini barnacles. This particular one right here is an owl limpet. Owl limpets are the largest limpets we have around here, and often you find actually other limpets that are attached to them, like you see for this one, little tiny limpets attached to their shell. Owl limpets are really cool, and they illustrate a really neat adaptation for space limitation. So as we're going to talk about in class, the primary limiting resource for organisms in the intertidal zone, the rocky intertidal zone, is space. Not food, but space. Owl limpets are really cool because they're territorial. Believe it or not, these things actually move around. What they do is they actually will etch out a little depression in the sediment. If you look at this rock, you'll see there's all kinds of little depressions, shallow depressions. Those are all made by limpets at one point or another. Some of them are occupied, some of them aren't. This owl limpet basically hangs out here during low tide when it's exposed, sealing itself to the rock so it doesn't dry out. And when the high tide is here and the water's over, this limpet will actually move around and defend its territory. So this is one illustration of interference competition or territoriality. This territory will probably be about the size of this sort of lump of rock, maybe a little bit less than a half square meter or something like that. It'll move around. It'll actually consume the algae that you see here on the rock, and it will defend its territory by knocking things off of the rock. It'll sort of slowly plow into them basically and dislodge them from a rock, keeping other organisms out of its territory around this limpet. And when it's done and the tide is receding, the limpet will go back into its home scar and live there until the next high tide. Here we can see one really neat adaptation to mechanical stress as well as predation. These are troglodyte chitons. They etch a crevice in the rock and remain there their entire lives as they grow. They feed by having water wash over them, and they filter out little particles from the water under their shells. This is a great adaptation for resisting the strong, powerful waves that come across the intertidal, because they really cannot be dislodged, either by a wave or by something like a predator. All right, so here we're in a tide pool microhabitat, and another adaptation that organisms use would be to live underneath algae or surf grass. So this green stuff is surf grass, a type of seagrass that grows in the intertidal zone. It's very, very well attached to the rocks. And we have some algae like sargassum over here as well. And organisms can basically use these plants and algae as a shield for drying out and heat stress. So living under this little microenvironment, preventing the sun from heating up the water is a really good strategy to help with heat stress. And organisms will sometimes be lost at the shoreline if we lose some of these plants and algae. So in your textbook, part of the reading for this module, at the end of the reading, talks about alternative stable states. And in places like Maine and Canada, where it can get very, very cold and icy in the intertidal zone, sometimes there are big, massive ice scour events where ice comes along and actually scours along the intertidal and wipes out all the algae and plants that you find in the intertidal zone. And that allows different types of organisms a chance to settle and colonize the area in the intertidal zone. And that actually changes the species diversity and composition to a great extent. So sometimes you can't actually predict what you're going to find in areas because a random event like a major storm and ice scour can actually completely change the composition of the intertidal community. Lastly, I don't know if Carl can get in really close, but if you look, I can see down here really closely, there are these little fish. I'm going to try to see if I can get them to move. There we go. Maybe you got that? Yeah. That was a tide pool sculpin.
There's another one on the left there.
These are adapted to, there we go. Right there's a couple of them moving around. adapted to obviously living in a tide pool. They're fish, but they hang out basically on their pectoral fins all day. Camouflage very, very well in the intertidal zone. And obviously are hunters, little predators for things that live in this little microenvironment.
One of the things that sculpin might eat are some amphipods. Here you can see two of them in the midst of some hanky-panky. And these are teeny little crustaceans. I see a lot of them in my eelgrass samples and spend an inordinate amount of time with them. But they rely on camouflage within algae or even camouflage next to other animals. So you can see this one with weird coloration blends in pretty well with those periwinkles. Hermit crabs have cut out the middleman altogether by co-opting the shells of a bunch of different species of gastropod. This gives them protection from both predation and from exposure. So some of them can even use their large claw, you can see there, as an operculum in the way that snails do to keep themselves from drying out. And this allows them to become one of the most abundant species in the intertidal here, where they roam around feeding on detritus. Like most crustaceans, the striped shore crab can only breathe when it has water on its gills, so you can see this one is kind of gargling water it keeps on its gills, which acts kind of like a scuba tank for it on land and allows it to survive for up to 70 hours exposed to the air.
So this is a great environment here in the low intertidal zone to talk about disturbance. Disturbance is a major force in the intertidal that dictates the number of species that we find and what types of species we find. So if we can zoom in down here in this area, this cobbly area, we can see a large variety of rock sizes. And so we have our small rocks like this here. We have our medium rocks, let's say maybe this one over here and over here. And we have, of course, very large rocks like the one you see over here and around me. And the key is that wave disturbance is going to disturb or turn over these rocks at different frequencies. As you might imagine, a storm comes in, even maybe not a stormy day, just maybe a high tide with lots of waves and wind, will roll these little rocks over all the time. Whereas a medium-sized rock like this might be rolled over only in a storm or a particular day where it's really, really windy and wavy. And a large rock like this is going to be turned over once, maybe only every several years in a major storm. Now, we had some storms recently with high winds and waves and big high tides that very well may have turned over a rock this big, believe it or not. In fact, you can see this rock here, all these the Serpulorbis and sandcastle worms that are here would live on the underside of a rock like this. So it's very likely this rock got turned over in our major recent storm. So why is this important? It's important because disturbance dictates the kind of species and the number of species we find in an area like this. And so this is a great illustration of the intermediate disturbance hypothesis. And that hypothesis says that small rocks are turned over all the time, and when they're turned over, all the organisms on that rock get crushed by the turning and the churning in the water. And therefore, that space opens up to be colonized. And so we only find species that are very quickly able to colonize surfaces and rocks on those small rocks. That's a low diversity of species. Our very, very large rocks are turned over hardly at all, maybe every decade or so, only once every decade. And that means that the organisms that are really good competitors for space are able to colonize and take hold and completely colonize the rock and take over and occupy that space for a long, long time. Therefore, our intermediate-sized rocks, or medium-sized rocks, are the ones that are turned over every so often, maybe once a year, a couple times a year, and those will be the ones with the highest diversity, because they will be a mix of competitive species like we find on the big rocks, and colonizing species like we find on the little rocks. So that's an illustration of the intermediate disturbance hypothesis. The fact that when we have disturbances happen at intermediate frequencies, we find the highest diversity because we mix the colonizing species with the good competitive species.
So you can see I flipped this rock over from that crevice there, and this is what the underside looks like. Lots of weird stuff.
And this is one of the weirdest. So this is a flatworm. You can see it's this really simple, small animal that is restricted to just the undersides of rocks, because if it was exposed, it would dry out like a potato chip. Its mouth is also its butthole. You can see its gut inside of its body, that dark brown branched area. And these teeny things can actually eat small barnacles and limpets sometimes.
Woo! Woo! I like it.
Brittle stars are another thing you're not really going to see unless you lift up some rocks. They hide during the day especially, and when they feed, they just let one or two of their arms out into the current to catch detritus and plankton. And they're pretty good at making a quick getaway.
All right, we're here in the low intertidal zone, and we found Dr. Hovel's favorite species, the California spiny lobster. And so you can see him poking his head out right there. I'm gonna zoom in. There he is. The antennae pointed forward in defense. He's found a cool crevice to hide in. Now, spiny lobsters are a major predator, not only in the subtidal kelp forest, but also in the rocky intertidal zone. In fact, what they do is they come out at high tide and they go in search of things like mussels to eat. Mussels are one of their favorite types of prey to consume. They also can consume barnacles, all the gastropods we've talked about and looked at here in the intertidal zone, and soft-bodied prey as well, like even things like anemones. So lobsters are a really major predator we find in the intertidal. They're actually not so abundant in the intertidal zone here in San Diego as we would have in other places like Catalina Island in California. We find most of our lobsters in the subtidal areas, but this one happened to be right here in the intertidal and found himself a little crevice to hide in until the tide comes up. And good luck to him. So in the same tide pool in which we found our spiny lobster, right next to it we actually found purple sea hare, Aplysia, and you can see its head over here. Its mouth underneath would be scraping away algae on a rock. Maybe Carl will put it back in its habitat and we can sort of watch it move around a little bit. We found this guy munching on some algae on a rock as we were looking at our spiny lobster, and very well camouflaged under the shadow of a rock. You can see the lobster antennae moving around back behind it. And here it goes now, gliding over the surface of the tide pool, finding some algae to eat. You can see its gills on its back. It folds over on its back where it would get oxygen. And it's going to go away and try to hide from us under some algae. Wow. All right, everyone. Well, we hope you enjoyed your tour of the intertidal zone, some of the organisms that we see and their ecology. So thank you very much, Carl, for getting this awesome footage and stitching it together. Carl is the video master. We're doing that later on this semester as well. And we're sorry we couldn't have you here today. It's a beautiful day, but these are the way things go. And yeah, we'll still have a good semester learning about all kinds of cool marine ecology.
The sea hare said it missed you guys.
Yeah, exactly. And the lobster, oh well. All right, well, goodbye everyone. We'll see you in class.